Okay, hello everyone. So we can continue with where we left last time, and we had to prove that the max function fx is equal to max of xi is a convex function in Rn. Okay, so this is not really the infinity norm. So this is so xi's can be negative also. So but this also, like, we can prove this. The results for the max can be used here. So what we want is f of theta x plus 1 minus theta y, and this is defined to be max I, and then this is theta xi plus 1 minus theta yi. Okay, and this is less than equal to max I theta xi plus max of 1 minus theta yi. Okay, so the max can be written like this separately. Okay, and this is theta max I, and then xi, and then plus 1 minus theta max I yi. So this is theta and max of xi, which is nothing but fx, plus 1 minus theta, and max of yi is nothing but fy. Okay, so this proves that this implies that f is convex. Okay, so main thing here is this thing. Okay, so for a max function we can write like this. So another problem is quadratic over linear. So this is defined as fxy is x square divided by y. That's why the name is quadratic over linear. And the domain is defined to be set of all xy provided y is greater than 0. So we define it like this. Then the claim is that this is a convex function. Okay, now remember that this is a two variable function. Okay, so there are two variables. So the function is of the form R2 to R. So if we take so to prove that it's a convex function, we are trying to use second order condition. So second order condition tells us that grad square fx is greater than equal to 0. Okay, if you see the previous case, we used the original definition of convexity, the line definition of convexity, and here we see that this is differentiable, so we want to use the second order condition. So we use the second order convexity. Okay, in the previous example, we could not use the second order convexity because the max function cannot. So first order or second order convexity can't be used because max function is not differentiable in general. Okay, so that's why we could not use the second derivative test here, but here we can use second derivative test. However, it's a function of two variable, real valued, but function of two variable. So we want to use second order convexity. That is, you need to check that grad square fx, okay, whether it's positive definite or not. So if we take we take the derivative of this, okay, so let us say the first derivative. The first derivative will be the gradient, which is del f by del x and del f by del y. So del f by del x, if we take the derivative of this partial derivative with respect to x, so this is 2x over y. And if we take a partial derivative of this with respect to y, then this is minus x square by y square. Okay, so this is the first derivative, and then if we do the second derivative of this, then we will get a Hessian. Okay, so this is Hessian. Okay, so here we know that this is del 2f by del x square, del 2f by del x del y, del 2f by del y del x, and del 2f by del y square. So this is del 2f by del x square. So we have done del f by del x, so we have to do one more of this. Okay, so we have to do one more of this, and we have to do this with respect to x, right? So derivative of this with respect to x. So this will be just 2 over y. Okay, and then we have to do del 2f by del by del x of del f by del y. So this one, so del by del x of del f by del y. So this is so we have to take a derivative of this with respect to x. So this is minus 2x by y square, and then we have to do del by del y of del f by del x. So del by del y of del f by del x, this is minus 2x by y squared, and del 2f by del y square. Okay, so del 2f by del y square is this one. Okay, so if we do this, then this will be so this we can write this as minus x square minus 2, and we have to take a derivative of this with respect to y. Okay, so x is like a constant, so minus x square comes out, and derivative of this with respect to y is minus 2 and y minus 3. So this is like 2x square by y cube. This is 2x square by y cube. So this is the Hessian, and we can write this in a little bit arranged form. Let us say I take the common 2 by y cube, because there is a lot of y in the denominator. So let us clear up the denominator. So this is y square minus xy. This is also minus xy, and this is x square. Okay, so now this can be written as okay, I don't have a space here. Okay, so this can be written as 2 by y cube, and I can write this in the form y minus x outer product with y minus x transpose. Okay, so this can be written like this. You can verify that. Okay, we can verify that this is like this. So this is like y square, and then minus xy, and then this is minus minus x. So the way it is written is like this: y minus x. So this is a column vector, and then you are multiplying it with the same, but in the row vector. So this comes out to be same as this. Okay, now if you see this, so this is called outer product. Okay, so we have seen inner product. Inner product is when you have row multiplying with the column. Okay, so that is inner product. And outer product is when you have column multiplying with the row. Okay, so this is called outer product. So we have seen, so we have this, okay. Now, so remember our, we should not forget that our goal is to say that the Hessian is positive definite. So our Hessian, which is now written in this form, okay. So now the question is whether this is a positive definite. So I will create some space for the remaining part of this, so that I can write. Okay, that should be enough. Okay, so what we have is the following. So we have that a Hessian, which is grad square f of x, turns out to be of the form 2 by y cube, y minus x, and y minus x transpose. So this turns out to be positive definite because y is greater than 0. Okay, so let me remove this also. I need more space. Okay, so this is positive definite, I claim. So any outer product is positive definite. Okay, so it's positive or semi-definite. Okay, so this is of the form some constant times u transpose, where the constant is this 2 by y cube, and this constant is greater than 0 because y is greater than 0, and u is y minus x. So claim u transpose is greater than equal to 0. It's positive definite. Okay, so this is true because if I multiply by x transpose u transpose x, so this I can write this as xu transpose yeah, so I can write this as how. So let me
XU transpose.
Yeah, so I can write this as x transpose u. Okay, so since I'm taking the transpose here, so I can write something like u transpose x transpose u transpose x. Okay, so this u transpose x will be x transpose u. So the u will get the first part because this is associative. Okay, and then you can have this u transpose x, which is this. So so this is norm of u transpose x. Okay, so this is norm squared. So this is like greater than equal to 0. Okay, this is greater than equal because norm is greater than equal to 0 always. So this proves that the Hessian is positive definite, and hence the given function is convex. Okay, so this is and then another question is log sum exponential. So this is like log of the sum of the exponential is convex on Rn. Okay, so how we will prove this log of the sum of the exponent. So there are 3 ways, if you recall, to prove convexity: the line definition, and then you have the first order convexity. So that was fy is greater than equal to fx plus grad fx transpose y minus x. Okay, for all x and y that inequality. That's first order condition, the convexity, and then you have second order convexity when the function is twice differentiable. So for instance, then in that case we have Hessian being positive definite implies convexity. So in this case we have we are given a function which is log of the sum of the exponential. Now we see that this is a differentiable function. Okay, so this is a differentiable. So what we may try is to maybe use the second order convexity. Okay, usually second order is easier if it is differentiable. So let us consider the case of n equal to 2, and later I will generalize. So for the case n equals to 2, fx is log of ex1 plus ex2. Okay, so this is the case when n is equal to 2, and we would like to first check what is the Hessian in the two variable case. So in this case we have del f by del x1. If we look at, then this is 1 divided by ex1 plus ex2. Okay, so this is the derivative of the log of x is 1 over x, and then inside we have to do this is the chain rule, right? So this is e to the and because we are taking derivative with respect to x1, so this is e to the x1. Similarly, we can take del f by del x2. So by symmetry, it will also look like this. So 1 divided by ex1 plus ex2 times ex2 here now. Okay, and then we can compute the second derivative because that's what we need. So del x1 square. So this will be using the quotient rule. Okay, so you can apply the quotient rule here. So the quotient rule, recall that fx, if it is of the form gx by hx, quotient rule of differentiation. Okay, quotient rule of differentiation. So if I have to take the derivative of f, then this is denominator into derivative of numerator minus numerator into derivative of the denominator divided by denominator squared. Okay, so this is the quotient rule. This is of that form because I have in the numerator I have a function of x1, and in the denominator also I have a function of x1. So if we do that, ex1 plus ex2 denominator into derivative of the numerator minus numerator into derivative of the denominator is ex1 and divided by denominator squared. So ex1 plus ex2 whole squared. And by symmetry, we also have del 2f by del x2 squared. In place of x1 now we will have x2. So this will be ex1 plus ex2. Now e to the x2 now minus ex2 times ex2. Okay, and then divided by the denominator square, which is ex1 plus ex2 whole squared. Now we need to compute the mixed derivatives. So mixed derivatives are del x2, del x1. So if we do that, so we have to do the derivative with. Please turn off the microphone. Yeah. So if we do it, so we have to do del by del x2 of del f by del x1. So this is the case, right? So we have to do the derivative of this with respect to x2. So again, denominator into derivative of the numerator with respect to x2. So that will be 0 minus numerator times derivative of the denominator with respect to x2 is just ex2. Okay, and divided by the denominator squared. So this is ex1 plus ex2 squared. By symmetry, we can also write del 2f by del x1 del x2, and this will be again following the same ex1 plus ex2 times 0 minus ex2 times ex1 divided by ex1 plus ex2 squared. It turns out that in this case, this is equal to this. The mixed partial derivatives are equal, and this happens when del 2f by del x1 del x2 is equal to del 2f by del x2 del x1. This happens when the partial derivatives are continuous. For instance, del f by del x1 del not 2 but just this del f by del x2 is continuous. Okay, then the mixed partial derivatives are equal. Okay, that's a result from the calculus. When the partial derivatives are continuous, then the mixed then the mixed partial derivatives are equal. So in other words, this will make the Hessian symmetric. Okay, so in this case, so it will make the Hessian symmetric. So assuming that all this is there, so now I will remove these things again and reuse the space. So we can now write down the Hessian. So Hessian in our case now is the following. So grad square fx in our case now is ex1 plus ex2 divided by ex1 plus ex2 whole squared, and this is times ex1, and this was again there was more term here minus 2 x1, okay, because there was ex1 squared here, and this term is minus ex2 plus x1, and here it's minus ex2 plus x1. So we have summed the exponents, and this is ex1 plus ex2 whole squared, and here ex1 plus ex2, and then ex2 minus 2, not 2, but e2x2, okay, divided by ex1 plus ex2 whole squared. So we have written down the Hessian. Now let us define z a vector like this, ex1 comma ex2. Let us define a vector like this so that we can compactly write these things. So I mean, not the z will be the sum of this, because ex1 plus no, okay, so z will be a vector only. Okay, so let me put z to be vectors, because then I will define a product. So then this implies that ex1 plus ex2, I can write this as vector of all ones inner product with z. Okay, in other words, I can write this as 1 transpose z, where 1 is the vector 1 1. Okay, so I can write this this compactly as 1 transpose z. So with this notation, what we can write for the Hessian now. So this implies the Hessian now in this new notation becomes, remember ex1 plus ex2, we have just written it as 1 transpose z. So here we will put 1 transpose z. Okay, so this is like 1 transpose z times ex1 minus e times 2x1. Okay, and then this is minus ex2 plus x1. So this term remains as it is, e to the minus x2 plus x1, and then we have 1 transpose z, and this is ex2 minus e2x2. Okay, so our Hessian now looks like this in a compact form. Now we also observe the following. So we observe that Z transpose is EX1, EX2. So and then like we are writing the outer product form. So this is like EX1, EX2, and this, I mean not outer product, but this is like a inner product form, because Z we have denoted is like a row vector. So it's like a row times column is a inner product. So this will turn out to be 2x1 plus E2x2. And we can also define the outer product, which is, I mean this is the inner product, and we can define the outer product, which is Z transpose Z. So in the Z transpose Z, we have EX1, EX2, and EX1, EX2. So if we do this, then this is E2x1, EX1 plus x2, EX1 plus x2, and then this is E2x2. Okay, so Z transpose will look like this. Right, so now what we can do is that we can write this in now compact form. Okay, so I keep running out of the, so let me rub this so that I get some space here. So now we have transformed everything into the Z variable. Okay, so that it will, we can write this compactly, and then we have to use, usually what we have to do is that we have to write this in some kind of inner product of the same vector so that it becomes greater than or equal to 0. Okay, the main trick here is to rewrite things in a way that we get to that. So if we so we notice that the Hessian can now be written as grad square fx. Now Hessian can now be written as 1 transpose z times diagonal of z. Okay, so 1 transpose z times diagonal of z will give you these values, this and then this. Okay, so 1 transpose z is already there. Okay, this is and then if you multiply by the diag of z, so diag of z is diag of, it's a diagonal, diag z means they make a diagonal matrix out of the vector. Okay, so for instance, so diag of z is EX1, EX2. So this is the diag of z. So if you multiply by 1 transpose z, then you will have 1 transpose z EX1. So you will get this first term, and 1 transpose z EX2. So then you will get this term. Okay, yeah. So I think I should say that you will get this term, and then you will get this term. And to get this remaining terms, we will get it from here. So if we subtract minus z transpose z, then yeah.
What happens to the denominator?
Denominator, we have to take it common, right? Because denominator is common everywhere. So we will keep the denominator separately. Because the denominator has no such role to play actually, because it's positive anyway. So denominator was here was 1 by e to the x1 plus e to the x2, and this is whole square. So this is always greater than 0. Okay, there is a denominator way here which is always greater than 0. Okay, so we can like, yeah, because yeah, we can like forget about that. Okay, that doesn't harm us here when we are proving the positive definiteness. Okay, so
just confirming the Hessian ones, shouldn't the like non-diagonal terms be like, suppose 1 transpose z minus e to the power x1 plus z2 upon 1 minus 1 transpose z square? Like there is one transpose z terms missing a few places.
yeah, I mean, yeah, you are right. I mean, I can put that. I can put that here also. Okay, so I can put the denominator explicitly like 1 by 1 transpose
Like
z
apart from
yeah.
Apart from the denominator also, it should be 1 transpose z minus e to the power x2 plus x1.
Yeah, so I'm coming to that, right? So
Okay,
right now
okay,
it's 1 transpose z and diag of z. So far what this recovers.
Hello, sir.
Yes. Yeah.
Sir, here you're considering 1 transpose z as e power x1 plus e power x2, right? But
Yeah.
1 transpose is a row vector and z also a row vector. How can you do multiplication?
No, we have I have defined 1 transpose z, right? 1 transpose z is ex1 plus ex2, right?
Yes, sir, but 1 transpose is a row vector and z is also a row vector.
No, 1 transpose
One
z
is a
is
row
not
vector.
not a vector. It's a number, right? It's ex1 plus ex2. It's not a vector, right? It's just some number now. 1 transpose z is not a vector. 1 transpose z is ex1 plus ex2, which is some number, right?
Yes, sir, I agree to that, but you're considering 1 as a column vector, right? So 1 transpose will be a row vector, and z also you assumed as a row vector. So you can't do multiplication between two row vectors. Are you doing dot product?
Yeah, so the way I define this is like, yeah. So 1 transpose will become a row vector, which is what I need. And z should be defined as a column vector. Yes.
No, wait.
Yeah.
One
So
is already in 2 cross 1 or n cross 1, right? So 1 transpose would be 1 cross n, and z is n cross 1. So it is not a problem. What problem I am having is in the non-diagonal elements of.
No, yeah, I'm coming back to that. Yes, I'm coming back to that. But yeah, there was a valid point here that. So let me do z as a column. Like, let us keep everything as column without ambiguity. So z will be by default a column vector. So I do ex1, ex2 transpose. Then it doesn't violate anything. So z is a column vector. 1 transpose is a row vector. So that will make this. So there is no ambiguity now. Okay.
Z transpose z will be zz transpose, sir. Here you consider z transpose z, right? It will be zz transpose, and zz transpose will be z transpose z.
Yeah. So there also we have to make some changes now, because we need a transpose now. So this will be now z transpose z, and this will be the other way around. So this will be
excuse me, sir.
z transpose.
Sir.
This is z.
So we are.
One second. So this is z transpose. Okay. So we have fixed the z. Now we take z to be column, and there is no ambiguity anywhere now. Z transpose z is the inner product, and z transpose is the column times row, which is the outer product. And so far what you see here is just the first term. Okay, and I have to adjust this now. Okay, so let me. So this is 1 transpose z. So 1 transpose z is this, which is we already had. Diag of z will make z a diagonal. So diag of z, if you want to keep in mind, then this will be ex1, ex2, and then 0, 0. So this is diag of z. So if I multiply by 1 transpose z, then I will get 1 transpose z ex1. So I get this term here. And then in this 2 term will be 1 transpose z ex2. And then I'm left with this. So the things that are left to be fixed are these terms, and this term. So we need to do something. Okay, so let me do. But what we notice is that these terms are actually available here in z transpose. So e2 x1 is there, but the negative of that we need. So if we take a negative of Z transpose, we fix the remaining terms. We do negative of Z transpose. Okay, so then we fix the terms, right? Now the question is, we did all this manipulations for what, right? We did this so that we can use the fact that norm of the vector is greater than equal to 0. Okay. Usually when you're proving positive definiteness, you have to do this. Okay, you have to do this trick. So we have vectorized it, and so what we have to prove now is the grad square fx is greater than equal to 0. Okay, so we have to prove that this is positive definite.
Sir,
so yeah.
The non-diagonal terms of grad square of the Hessian, couldn't they be simplified further? Like if I expanded it, like e raised to x1 plus e raised to x2 multiplied by e raised to x1 minus e raised to 2x1, doesn't it simplify further into e raised to x1 plus x in power x1 plus x2, and as it don't those terms cancel out?
Yeah. Yeah, the question is like, yeah, the question is like we can I mean, look, there is nothing common as such here. Neither ex1 is common in all the term, neither ex2 is common in all the term. So taking common won't help here. Yeah, just taking common won't help, and we cannot write this as a sum of sums because the sum is in the exponent, not in the terms. So
So like 1 transpose Z is e raised to e power x1 plus e power x2, which when multiplied by e raised to x1 would give me e power 2x1 plus e power x1 plus x2, and the e power 2x1 terms cancel out.
Yeah, actually e to the 2x1 terms will cancel out, yes.
And in that case, we can just take out e power x1 plus x2
we
common
can take
out of the entire
determinant. We can take the determinant, and I think determinant will turn out to be, yeah, so we can also do it that way. So let me do it that way, like what you're saying, and we can also do it the way that I'm doing. The way I'm doing is actually interesting because this trick will be used in other problems, you will see. So the way like the Arpan is describing right now, we can do this. Actually, that is a little bit easier route, but there is a motivation behind doing this. But let me do the way he's saying so that you have two different ways. Okay, so remember the Hessian was grad fx was let us like, okay, I mean, let us not write it in one transpose Z form so that we can see explicitly what is happening. So ex1 plus ex2, and then this was ex1 minus e2 x1, and then here we had minus ex1 plus x2, and here we had minus ex1 plus x2, and here we had ex1 plus x2, and then ex2 minus e2x2. Okay, so what Arpan is saying is like these guys will get e2x1 will get cancelled here, e2x2 will get cancelled here. So if that is the case, then what we have here is x1 plus x2. Okay, this is like simplified form, right? So minus e again x1 plus x2, and here again minus x1 plus x2, and then here x2 gets cancelled. Okay, one ex2 gets. 2x2
So this
gets
seems
cancelled.
simple for n equals to 2, but suppose it is n equals to 3. So it would be e to the power x1 plus x2 plus e to the power x1 plus x3 and kind of these things. So it would be more complex here. Like for n
Yeah.
equals to 2 is just simpler.
Yeah, let us see what happens for n. Yeah, so let us, in this case, let us simplify it. So this is like e x1 plus x2. Okay. So so what we see is that e x1 plus x2 can be taken common actually here. Okay, so we can take common and that will simplify. Take common, and then if you see the common term is positive, e x1 plus x2 is positive, and then we take the determinant and determinant of the remaining matrix. This will be like positive, and then the whole thing will be positive because the matrix will be positive definite if the determinant is greater than 0, right? So that's the plan here. So we can take e x1 plus x2 common, and this is like 1 minus 1, okay, minus 1 1. Now this is positive, so now the positive definiteness depends on this matrix now, but this matrix is positive definite because the determinant of this is determinant of this is 1 and then plus 1, so this is like 2, right, which is greater than 0, right? So
The determinant is 0, sir.
Okay, determinant is 0, right? Yeah, determinant is 0 actually here. Yeah, because 1 and then minus 1. Okay, but it is still fine, right? Because okay, well then let us do it in the other way, right? Because determinant is 0, and let us do it. So let us do it in this way.
We can write it as a
Outer product.
outer product
Outer
of
product.
1 minus 1 1 minus 1.
1 minus 1. Yeah, let us do this way. So 1 minus 1 1 minus 1. So this comes out to be this matrix. So this is of the form U transpose, and any matrix of the form outer product U with the same U transpose is must be greater than or equal to 0 by the previous argument. So this will work. Now the question was, and then before this the question was, what will happen if we have the general case where we have x1 plus x2 plus dot 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 plus
But even
xn.
in general case, determinant
So,
UU transpose will be 0.
no, so I've generalized the form. So in the Hessian term.
So here in the Hessian, you have to say what would be the generic form. So if I start writing,
yeah,
in the general form, it will be it will be form like this. Okay, Control Z. Yeah. So this will be ex2 plus dot 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 plus exn here, and then you will have ex1 term, right? And then minus, you will have e2x1 again, right? In the general form. Can you extrapolate this? So so
it would be like
2x1 will get cancelled again, I think, right? And what you will be left with is, yeah, so in the general form, what we will be left with.
Okay, so should I say for if I equals to j, it would be summation of e to the power xi plus xk, where k is from 1 to n excluding I, and when I not equals to j, it would be minus e to the power xi plus xj. This is it.
Yeah. So to prove the general form, we have to first understand what are the terms here, right? So what are the terms here? So I believe this is x1 and then minus 2x1 again here. So this will be this term, and then this term will remain similar. It will be minus of x1, x2 up to xn. And this will be similar. And then by symmetry, this will also look like this, but it will be with x2, right? And then so are we sure to take common like we did it here? Like, are we having
no, sir, we
something?
can't take it.
We won't be able to take common like we did it in this case, right?
Yeah, we can't take.
Hmm.
Sir, also
Hello,
now, how are we proving the convex thing?
Yeah, you won't be able to take common like we did it in that 2 case. Yeah.
And also for general n, it will be n cross n matrix, right?
Yeah, it will be n cross n. Yeah, exactly. You are right. So it will be n cross n. There will be a lot of terms here to fill. We are just trying to guess the general pattern. General pattern, we are clear, but the problem is that it is no longer that simple. Okay, so then we go back to the form that we were trying to go. In the 2 case, it's fine, but in the general case, this whole thing still remains. In the general case, that can be verified. Now, as I said, like our goal is to prove that this is positive definite. Okay, this is positive definite. So this is the trick. This is the tricky part in the sense like we have to use something which is called Cauchy-Schwarz inequality. Okay, so we have to show that this is positive definite. So we have to multiply with, let us say, some let us say some x transpose. Okay, we should not mix the same x here. Okay, so let us say we multiply with v transpose grad square fxv. Okay, so if we multiply, let us see what will happen, because we have to check. So we have to check v transpose grad square fxv. Okay, so this will be equal to this thing will remain 1 by 1 transpose z whole square, and then these guys are like summation of zi. So let me write this like this now: I equal 1 to n, and the v that you have multiplied here will get multiplied from the left with v, and it will also get multiplied from the right with v. So the net effect will be
Vi square zi.
Yeah, so you have v from left side, v from right side. So you will have here. So this is bracket parenthesis like this, and you will have here vi square zi, I equal 1 to n. Okay, this is the effect of v multiplying from the left, v multiplying from the right. This was a constant that comes out, and this is also like a constant because this is just sum of numbers, some zi. So this guy and this guy is a constant, so they can remain separate. So it's like effectively asking what is the effect of v diag of zv, because other things, 1 transpose z, 1 transpose z, they can come out because constants come out. So this is the thing that is written here. It will become vi square zi. Okay, and then if we look into the second term, and where we are multiplying from the left v and multiplying from the right v, so this will turn out to be, well, if you look into this term, then this is v transpose z, z transpose v. Okay, so this we have seen before. So this is like z transpose v transpose z transpose v, right? So basically this is the norm of z transpose v. So here we have to write the norm. So 2 norm of z transpose v will be like zi vi terms. So the terms here are zi vi in the vectors, right? So this will be like vi zi or zi vi. Okay, it doesn't matter. So this whole thing squared. Okay. So this is the norm of z transpose v is this term. Okay, so I mean, this is equal to norm squared, right? So this is like this. Okay. So
Hello,
Vi,
sir.
yeah.
Sir, it should be summation of VIZ square, right? Not summation whole square.
Now, isn't it that this gets summed like Z transpose V?
It's scalar anyways.
Yeah, Z transpose V is like a scalar, right? Yeah, so it's like scalar actually already. These guys are not really a vector anymore, right? So these are like scalars, so they get like ZV squared actually. Okay, so this is like Z1 V1 plus Z2 V2 plus Zn Vn. And this is the same thing. Z transpose V is same as, and this is a number. So transpose of that is the same thing. So this is like the number squared. So this is like this squared. That's what we written here. Okay. So this is what we have, and this is where the main part comes here. And this trick is used a lot in many papers and so on. If you can move your problem into this form, then what you have to visualize is something called Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality is the following. So this is usually taught in linear algebra. So Cauchy-Schwarz inequality. So that says that for any vectors A and B, A transpose A times B transpose B is always greater than or equal to A transpose B squared for all A, B. Okay. So this is the result which is called Cauchy-Schwarz inequality for any vector A and B. I think this is there in, maybe this is there in the assignment, or maybe maybe an application of this is there in the assignment. But for us, it's enough to just recall this. I mean, remember this. So A transpose A times B transpose B is always greater than or equal to A transpose B whole square. This inequality may look innocent, but actually it can be used to prove some very difficult looking inequalities. Okay. So now now we have to identify what could be A and what could be B in our case. Okay. So if we see here, we want to use the inequality here. In other words, we have to prove that this guy is greater than or equal to this guy. Then the whole thing will be greater than or equal to 0. So we have to identify somewhere A here, somewhere B here, and then A transpose B somewhere here we have to identify. Okay. So now the whole focus goes into finding what is the suitable A, B, so that Cauchy-Schwarz can be used. Okay. So what could be the possible A and B vectors? Okay, that's what we want to see now. Okay. Okay, so you may have to manipulate a little bit. That's what I'm trying to say. It's like you may have to manipulate, maybe take some square root of some of the terms, something like that. Okay, and make sure that this is in the form of Cauchy-Schwarz. Okay, if that is the case, then we are done. Okay, so what do you think?
We can take A vector as under root Z1 under root Z2 and B vector as V under root Z1, V under root Z2.
So
Yeah.
I'm sure that we can take under root of left hand side, but we can't probably take under root of right hand side always, because like Zi is always positive, but Vi can be anything.
Yeah, so Vi we should not take Vi we should not take square root. Yes. So
but Vi is already in the square form, right? So we don't need to take a square root of Vi.
No, in RSS
Yeah,
it
exactly.
is not, right?
Exactly. So Vi you can keep it. You can take Vi and then square root of Zi, and yeah, so that will work. It's just a little bit of let us see that now. So let us take AI to be AI to be, I propose Vi square root of Zi, and choose Bi to be square root of Zi. Yes. So with this, what is A transpose A? A transpose A, let us see what is A transpose A. So A transpose A will give you this term, this one, Vi square Zi, I. And if you check B transpose B, B transpose B will give you this term, Zi, I equal 1 to n. And A transpose B will give you this term, which is Vi, because Zi square root, and it will become Zi. Okay, so A transpose V will be sum of this. It's not the square, but just A transpose B is this. And then we have to take the square. So this is the squared form that we need. So this is indeed in the form with this choice of A and B. So from this, from the Cauchy squares, we are now immediately sure to say that this is grade square fx is positive definite. Okay, so that's how we do this. And this I spent time on this because this is the trick that is used a lot in proving convexity. Because so Cauchy, either you can use it Cauchy squares form, or either you transform something in the form of U transpose, then this will be norm, and then this is greater than equal to 0. So these are the two main ways for a vector, for a multivariable function. These are the two main ways you can prove these inequalities. Okay, so that's where, okay. So this is convex, and that's what we have proved already.
Hello, sir.
Yes.
Hello, sir. So once can you explain the relation between the Cauchy squares inequality to the del square fx greater than equal to 0?
Relation of Cauchy squares with
Our requirements, sir, del square f of x greater than equal to 0.
Yeah, so we have done it just now, right? So this is what we have to prove, that for any v, we have to prove that this is greater than equal to 0, right? So I multiplied with v on p transpose here and v here, and then v went inside, and here v went inside, and then we have to prove.
Okay, so basically, if you bring the left hand side to right hand, it will be greater than equal to 0. Yeah, yes, I got it. Yeah.
Yeah.
Yes.
So this is like B transpose B. Okay, and this is A transpose A, right? This one, and this is like A transpose B whole squared. So B transpose B times A transpose A, or A transpose A times B doesn't matter because they are numbers, so they can commute. So this by Cauchy squares must be greater than equal to A transpose B whole squared. So hence this term is greater than equal to 0, and this term is anyway greater than equal to 0, because this is sum of exponents. So sum of exponents can never be 0. Less than 0, right? Cannot be less than 0. So from there we know that this guy is greater than equal to 0. Hence grad fx square is positive definite, right? So this symbol means positive definite, right?
Positive semi-definite.
Positive semi-definite, yeah. So that was the proof of that. And in the similar vein, there is another example where we have to prove that geometric mean is a concave function. Okay, so it's not convex. In other words, the negative of the function is convex. Okay, a function is concave if the negative is convex. So we can try to do this as well. So let us try to do the. So without going into too much of nitty-gritty here, what I will do is that I will write down the derivatives, and I leave it as an exercise for you to check the derivative computations. Okay, so del 2 f by del x k square, let us say with respect to the kth component, I claim is that this will be n minus 1 product of xi I equal 1 to n, and then this 1 by n divided by n square xk squared. Okay, so I let you compute these this derivative, and then I claim that mixed partial derivative, which is del xk del xl, will be product of xi I equal 1 to n 1 by n divided by n square, and then xk and xl for k not equal to L. For k equal to L, we have already done this. So, and then xl xk will be same, okay, because of the fact that these del f by del xk are continuous. Okay, so that's the mixed partial derivatives are equal when the single derivatives are continuous. Okay, so which is true in this case because we are in the domain R++, so it is well defined. We can do infinitely many differentiations and so on. So it's continuous and differentiable and so on. And so in this case also we would like to put this in a vectorized form. So let us see what we can do here. So in this case, grad square fx. So do I have a space here? Okay. Oh, actually I have written this already here. So let me work from here only. Okay, so I have already. So these are the Hessian kk component and these are the kl component, which I also wrote in the previous slide. So I can write the Hessian in this form. You see, this is the vectorized form of the Hessian. So you take out the terms that are like common in both the mixed and the non-mixed part. So this is the term that is common here, and that is the term that is also common here. You take that common. Okay, you can also take the negative common. Okay, and then what you are left with are terms of the form. So the terms. So on the diagonal, if you also see this in terms of matrix, if assuming that I have taken out this common, and okay, and there is n minus 1 also left here, right? So what is left here after doing that is n minus 1 and divided by x1 square. The second diagonal term is n minus 1 divided by x2 square. Okay, and so on. So these are about the diagonal terms and so on. And what is left in the off diagonal terms are 1 by xk xl type. Okay, so in other words, the first term in this case will be k will be 1, right? So 1 1 2 1 3 1 4 so on and then so on. So this type of terms are there in the off diagonal terms. So we are again trying to rearrange things in certain way. So what we are trying to do here is that we have taken since if you forget other things, then on the diagonal we have terms like this x n square. So we make a diagonal of this. So we make a diag of this. So diag of the vector that will become a matrix like this. So that will be this. Okay. And what we are trying to do here next is minus QQ transpose. Okay, minus QQ transpose where Q is 1 by xi. So what is being claimed here is that will take care of the off diagonal terms. So why is that? And this is the outer product form, right? So it is the outer product form and Qi is 1 by xi, right? 1 by xi. So if I do QQ transpose, right? So this is like the column times the row. So 1 by x1, 1 by x2, 1 by xn. And this is 1 by x1, 1 by x2, 1 by xn. So this will give us what? 1 by x1 square. So on the diagonal term, it is giving us those terms, right? 1 by x2 square and 1 by xn square. And the off diagonal terms will look like 1 by x1, x2, and so on, right? 1 by x1, xn. And here it will be 1 by xn, x1, and so on. So these are the terms that are there. Okay, so if we look into this, and then if we subtract these terms, right? So this will take care of these terms, right? So xk, xl terms will be taken care of. Okay, so since we have taken the negative, so this negative will be also taken care of by, because negative will make these terms positive. Okay, now do you see this n minus 1? Like, how is this n minus 1 being fixed here? Okay, so what we have taken common, like why we should end up with n minus 1 here? Like, do we have anything to suggest that we will have n minus 1?
So for diagonal values, q force will be 1 by xi square. So if we subtract it from this term, it will be if we take 1 by xi.
Okay, so what we are trying to say is like we are subtracting n 1 by xi square and then 1 by xi square, right? So this will give us n minus 1 by xi square, because n 1 by square terms are given by these guys, these terms, and then this qi transpose is subtracting just 1 by xi square. So if we do this subtraction, so if we go back these guys, so this is q transpose term is here. So the q transpose terms have this just 1 by x1 square, 1 by x2 square. So if we subtract those from these guys, then we will be left with n minus 1 by x1 square and so on. So n minus 1 is taken care of. Okay, so I hope you can see n minus 1 is taken care of. And then the remaining terms are fine, because there is just n square here, and off diagonal terms are anyway 1 by x1, x2, and so on. So those terms are taken care of correctly. Okay, now after all this, you can also, if look at offline, this is just a simple algebra here, but important thing to note is the way we vectorize things and put this in some form, right? So again, you can see from the form here that we are trying to somehow use Cauchy-Schwarz. Okay.
So could you once again tell how we'll be using Cauchy-Schwarz here? Like I didn't get it. How will be what we'll be doing of n?
What we are doing of n? Like which part you are? Cauchy-Schwarz I have not discussed yet, right? Up to here,
Okay,
you are
okay.
clear, or?
Yes. Okay. Clear.
Okay.
Okay,
Up to here, you are clear, right? Okay. So if we do now, so to check that this is a symmetric and positive, this is like always symmetric anyway, because Aij is Aji. So we have to check that this is like positive definite. So we multiply by V transpose V. If we multiply by V transpose V, then we have to see where V goes, right? So this is a constant. So this constant stays out, and then V enters here, and V also enters from the right hand side. So if we do this, then you have Vi square by Xi square, and this n is the same n here, minus, and then if you do same like before, V transpose Q transpose V, so that will be like this. Okay, because Q are 1 by Xi, and then V from both sides, so this will be just Q transpose V square, which is this. Now, the thing is like how the Cauchy-Schwarz is used here. Okay, so now you have to tell me what is A and what is B. And Cauchy-Schwarz, if you recall again, Cauchy-Schwarz was A transpose A times B transpose B is greater than equal to A transpose B whole squared. Okay, and remember that in this case, we have to prove that this is positive. If this is positive, then negative of that will be negative, right? So there is a negative outside. So it is enough to prove that this is greater than equal to 0. And this negative will make sure that this is less than equal to 0. So what we have to prove is that this is greater than or equal to 0. So how we can prove this? What should I choose, A? And
So we
what
can
should I
take
choose?
A as one vector and B as a Vi by Xi vector.
Okay, so let us try. So choose A to be just 1. It's like the vector of all ones. And B vector whose ith component is Vi by Xi. Okay. So what will happen in this case? So what is A transpose A in this case, right? So A transpose A will turn out to be just N because it's sum of N, right? So this is just N. And B transpose B will be what? B transpose B will be Vi square by Xi square, right? Because B is Vi Xi. So this is sum of Vi square by Xi square. Okay. And then A transpose B will be what? Right? A transpose B will be the sum of these, right? So will be the sum of these Vi and Xi, right? So this will be sum of Vi by Xi. Okay. I mean, yeah. So Cauchy-Schwarz says that A transpose B whole square, which is this guy, is greater than equal to this times this, which is exactly the form that we need here. So this guy is A transpose A times B transpose B. Okay, so this is like A transpose A is the N part, and B transpose B is the sum of Vi square by Xi part. Okay, so this is like from Cauchy-Schwarz we have that this is greater than equal to 0. Okay, so this choice of A and B is sometimes tricky. This comes from practice, but indeed we can like think a little bit, and usually we can prove this. Okay, so yeah, so this is the so in this case we have proved that the V transpose Hessian is negative definite. So since the Hessian is negative definite, it is concave, which is what we have to prove. Okay. Okay, so yeah, this is what I have written here. Okay, so let us look into this matrix function. Okay, so we have not seen matrix function yet, I think. Okay, so sometimes one may ask, this is a function of a matrix where X is a matrix. Okay, then prove that this is a concave function, and this is a matrix function, right? So how we will prove results like this, right? So it's log of the determinant of X. This is a matrix function, so it's going from R m by n to R. So it's taking a matrix X and it is giving you a number log of determinant of X, because this is a number and log of number is a number. So this is a matrix variable in the matrix, and then outcome is a real number. So how do we prove that this is a concave function? So here we will invoke a property that we have discussed some time ago, which said that a function is convex if and only if it is convex when it is restricted on arbitrary line. Okay, so this is the result we have proved before, and these results can be used to especially prove a very high dimensional problem like functions defined on matrices, right? In those cases, these results are very useful. So to prove that this is a concave, and remember, these are not very random functions I'm talking about. These functions show up in research, okay? So you will very likely see these problems in research. So to establish that this is a concave function, what I will do is I will invoke that result, that I will choose arbitrary line and prove that the function is convex when it's restricted on a line. And by line, I mean joining 2 points in my domain. And here the points in my domain are matrices. OK, so here the points in my domain are matrices. As I said, the concept of point is very general. OK, I can take 2 cats as points, 2 dogs as points. It depends how do I, as long as I know how to add 2 points, subtract 2 points, it's fine. OK, algebra is defined, then it's fine. So in this case, the line joining 2 points will be of the form x is equal to z plus dv. OK, this is the line joining 2 points in the domain. Domain is the set of matrices. OK, and it is also given that this function is defined on defined for positive definite. So this is like positive definite. OK, so the domain is set of all Rn to R, where domain is the set of all positive definite matrices. The reason why we take positive definite, because log will be defined only for those. I mean, it's safer to define log for those. Otherwise, at 0 we don't have. It goes to like minus infinity, right? So that's why for safety we say that it's positive definite, so that the determinant will be some positive number, and then we are always taking log of the positive values, which is well defined. Log is well defined for the positive values. So that's why we take positive definite. So a arbitrary line joining 2 points will be. Yes.
Sn, those are the matrices of a size n cross n.
Yeah, so these are symmetric matrices n by n. Symmetric n by n and positive definite. OK, so these things are like given here. OK, because yeah, so positive definiteness is like defined for symmetric. OK, because rectangular matrix, yeah, I mean, we don't have these concepts of like eigenvalues and so on. So here we assume that the domain is symmetric. OK, so I should actually write n by n, because determinant is only defined for symmetric, right? So more precise way to say is like this is a function from Sn plus a set of all positive definite matrices. It's like positive definite is like 2 plus, OK, and 2R. OK, the domain is the set of all positive definite matrices, symmetric and so on. OK, so we will take arbitrary points, which are in this case matrices.
Why should it be symmetric? This determinant can be for all square matrices, right?
Yeah, we can define for all square matrices, yes, but positive definiteness. The concept of positive definiteness is defined for symmetric matrix. OK, so here we are already given that it's like it's a positive definite, and then we want to make sure that the log is well defined. OK, so yeah, I have something to add with respect to positive definiteness and why, although the initial definition does not say that A has to be non-symmetric. OK, but you will see that positive definiteness makes sense for only for symmetric. OK, because then otherwise you have like complex eigenvalues and so on. So so usually when we define positive definiteness, we take symmetry as well. OK, and so it's I mean by symmetry here, I also mean like it's like square matrix. I mean square matrix. Sometimes I'm mixing symmetry with square. OK, so determinant we need because it's it is only defined for a square matrix. So that's why we have n by n. And log is defined for positive value. That's why we are also trying to make sure that it's positive definite, and positive definiteness is defined over symmetric matrices. OK. So that's why we need all this. OK. There is something interesting here. So what will happen if it's not symmetric, right? So a matrix A can be split into two parts, right? So how we can split a matrix into symmetric and skew symmetric matrices, right? So I can write this as A plus A transpose by 2 plus A minus A transpose. Is this correct? This is correct, right? So I can write any matrix A like this, right? Now what you observe is that this is symmetric. OK, so this is the symmetric part of the matrix. Symmetric part of A. So any matrix, let us say non-symmetric now, obviously, because if it is symmetric, then yeah, I mean this will get cancelled anyway, and this will just become 1. If it is not symmetric, then this part is not going to cancel. So this part is called the skew symmetric part. So what will happen if I do a V transpose AV? Because for positive definiteness, what I want to check is like this: V transpose AV, right? So this will be what? Half of V transpose A plus A transpose V. And this will be half of V transpose A minus A transpose V, right? So what do you see from here? What do you observe when I write it like this? Do you see something? Is there something cancelling here?
Yeah, V transpose.
Yeah. You see, so this part is getting cancelled, right? So this is why positive definiteness doesn't really make sense for none, because the non-symmetric part, that was this part, is hardly contributing anything. At the end of the day, you are
No, if we
only
find determinant of that, it would be cancelling, right? Otherwise, it is not outright cancelling, or is it?
Yeah, I mean, if you go by the usual definition of the positive definiteness, what you end up with when you're testing V transpose AV, when you're testing your V transpose AV, you are testing it ultimately for the symmetric matrix only. OK, because the non-symmetric part, which is only because of this part, because A plus A transpose is a symmetric matrix, right? Because A transpose is A transpose plus A, which is A plus A transpose. So this is a symmetric matrix. So this is why in general you see that in practice testing it for non-symmetric matrix, you end up testing V transpose V only for the symmetric part only, symmetric matrix only. OK, so that's why positive definiteness makes sense only for the symmetric part. OK, so I gave you one hint of why when we talk about positive definiteness, symmetry comes with it. OK. OK, so we have 2 points here. OK, so let us OK, so we have like 4 minutes left. Yes. So hello.
Sir, you just now said half of V transpose A minus A transpose V is 0, right? What is the reason?
No, the reason was simple, right? Is it not saved now? OK. No, so it's not saved because so So this is like V transpose, and then half we take outside. So let us say half, and then V transpose A minus A transpose V. So this is like V transpose AV minus V transpose A transpose V. But these are the same number, right? Because this is a number and this is a transpose of the number. So it's like the same number. Okay.
Okay,
So
okay.
they will get cancelled. They get cancelled, right? So this is why. So I think we need some time here. So in the meantime, you can already think. So the proof that I'm going to do is to use the fact that I will take a line joining 2 points. So this will be the arbitrary line because I've taken Z and V to be arbitrary positive definite matrices. And then on this line, I will define a function gt that is defined only on this line. And then it will become a single variable function. And then for single variable function, I will prove that it's positive definite using double derivative of g. And then that will, and since Z and V were arbitrary line, that will prove that the function f must be convex.
Is t between 0 and 1 or anything? Any?
No, t is arbitrary. T is like indefinite line joining. Yeah. Passing through. Passing through Z in the direction of V. So you take arbitrary within the domain. But the domain would be it should be until. But the domain does not restrict your t to be arbitrary because for any t like positive, it will remain positive definite. So all the line that is possible in your given domain, you take the line as far as possible in the given domain until the points on the line, which is Z plus TV, which is the matrix that remains positive definite. Then take that and then prove that it's positive definite. So to prove that it's concave, right? It's a concave. So we will see this in the next class. Yeah. So I think with that I can stop. Yeah.